from Physics Department. Today I will explain the concept of Newton's laws and applications of Newton's law in the projectile motion. Welcome to all SYBSc students under video lecture Department of Physics Choice Based Grade System SYBSc semester 3rd. Name of the paper Electronics and number PHY 232 having credits 02. Now today we will study the types of a transistor and its symbol. Now the transistor consists of two PN junction diodes, and these two PN junction diodes form by sandwiching either P-type or N-type semiconductor. Now these three terminals are known as emitter, base, collector respectively. Now the emitter is heavily doped so that it can emit or inject large number of charge carriers into the base. Therefore, the emitter is a heavily doped. Now the emitter is also used to supply the majority charge carriers. Now next one is a base. Base is very thin and lightly doped. The base is a region through which the majority charge carriers pass and reaches to the collector. Last one is a collector. The collector is always moderately doped. It is large in size in terms of the area. Now it will collect the majority charge carriers supplied from emitter through base. Now this is the diagram which shows the two type of a transistor, NPN transistor, PNP transistor, the base, emitter and collector. Now these are the different types of a transistor in the market. Now we see the working of PNP transistor. Now see the in the diagram which is given below. So when the emitter base junction is a forward bias, when emitter base junction is a forward bias and collector base junction is a reverse bias. So this is the basic condition for any type of a transistor, whether it is a PNP transistor, whether it is an NPN transistor. The emitter base junction is always forward bias and collector base junction is always reverse bias. Now as the emitter base junction is a forward bias and we know that the emitter is heavily doped in the P region, therefore the large number of holes, so in the P region the majority charge carriers are holes, therefore the large number of holes start to flow towards the base and this will constitute the emitter current I. Now the base is thin and lightly doped. Therefore the holes emitted from the emitter region flows through the N-type base, because base is N-type in case of the PNP transistor. Now what happened in this case is that in this process very few holes less than 5% combined with the electrons and creating the valence electrons, and these valence electrons flow down into the base terminal and it will constitute the base current IB, and remaining number of holes nearly about 95%, because holes are the majority charge carriers. Now the remaining number of holes nearly about the 95% cross over into the collector region, which constitute the collector current IC. That means the remaining number of holes cross the boundary of a base and enter into the collector region, and that will constitute the collector current IC. As the collector region having physical large area, as you know that the collector having physical large area, and that's why the collector region having physically large area, and therefore almost all holes crossing towards the base are collected by the collector, and from this we see that the emitter current flow through the collector except very few through the base, and hence we can write very important equation: emitter current is the sum of the collector to base current. So this is the simple working of a PNP transistor. If you understand working of a PNP transistor, then it is very easy to understand the working of a NPN transistor. The working of a NPN transistor. So as you know that the emitter base junction is a forward bias, collector base junction is a reverse bias, and as the emitter base junction is a forward bias, and we know that the emitter is heavily doped in the end region, we change the region in the end region, and therefore the large number of electrons here, large number of electrons, because in case of the NPN transistor, the emitter is a N-type, and therefore in case of the N-type, the majority charge carriers are electrons, and therefore the large number of electrons start to flow towards the base, and this will constitute the emitter current IE. Now, as we know that the base is very thin and lightly doped, and therefore the electrons which are emitted from the emitter region flow through the p-type base. Now base is a p-type. Now in this process, very few electrons, nearly about the 5%, recombine with the holes and creating the valence electron, and this valence electron flows down into the base terminal, and which constitute the base current IB. And the remaining number of electrons, nearly about the 95%, cross over the collector region, which constitute the collector current IC. And as we know that the collector region having physical large area, almost all electron crossing towards the base are collected by the collector, and for this we can see that the emitter current flow through the collector except very few through the base, and hence we can write once again the emitter current is the sum of the collector and base current, and that is the equation I is equal to IB plus IC, very important equation we have here. Now we see the transistor configuration. So there are three types of transistor configurations. Now first configuration is common base configuration, we called as a CB configuration. Second configuration is a common collector configuration, we called as a CC configuration. And last one is the common emitter configuration, we called as a CE, common emitter configuration. We see one by one. common base configuration. Now see the diagram, common base configuration. Now its name suggests that the common is the base. So if you see the diagram carefully, the base is a common, or it is also called grounded base configuration. It is also called the grounded base configuration. Now in this configuration, common is a base, and this common base is common to input signal as well as output signal. So the base is common to both input signal as well as output signal. Now the input signal is applied between transistor base and emitter terminal. So the input signal, if you see the diagram carefully, the input signal is applied between transistor base and emitter terminal. Why? Corresponding output signal is taken between base and collector terminal as shown in figure. Now the base terminal is grounded, which can be connected to some fixed reference voltage point. Now this type of configuration provides low input impedance while it offers high output impedance. Although the voltage is high, the current gain is low. Therefore, overall power gain is also low. Now in this configuration, input and output are in phase. So these are the characteristics of a common base configuration. Then common collector configuration. In common collector configuration or grounded collector configuration, it is also called the grounded collector configuration. The collector terminal is common for both input and output signal. So that's why you common the collector terminal, and that's why the collector terminal is common to both input and output signals. Now the input signal is connected directly to the base, while output is taken from emitter load as shown in figure. Now this type of a configuration commonly known as a voltage follower or emitter follower, because emitter voltage follow the base voltage. So this type of a configuration is commonly known as a voltage follower or emitter follower, because the emitter voltage follow the base voltage. Now this is the second type of a common collector configuration, that is CC configuration. Now common emitter configuration. So this type of a configuration is practically used in the every majority electronic circuits. Common emitter configuration, C configuration. Now in case of the common emitter configuration, which is very useful for the impedance matching application. The common emitter configuration is useful lot of practical applications, and it is useful for the impedance matching application. It has very high input impedance while it having a relatively low output impedance, and that's why it is used in the impedance matching. Now in this configuration, we use emitter as a common terminal for both input and output as you see in the common base configuration, as you see in the common collector configuration. Here also the emitter is a common terminal for both input and output. Now here input is applied between, if you see the diagram carefully, the input is applied between base emitter region and output is taken between collector and emitter terminal. Now in this configuration, input parameter are VB and IB, and output parameters are VCE and IC. These are the input and output parameters. Now this type of a configuration is mostly used in the application of a transistor base amplifier. In this configuration, the emitter current is equal to sum of the small base current and large collector current, and that is I is equal to IB plus IC. So these are the three types of configuration: common base configuration, common collector configuration, and common emitter configuration. Now we see the relation between alpha and beta, very important as far as the transistor is considered, the value of alpha and value of beta. So what is meant by the beta and what is meant by the alpha? So these are the two current amplification factors of a transistor. These are the two current amplification factors of a transistor, we called as alpha and beta. Now the base current amplification factor beta. So you define the base current amplification factor beta. Very simple definition we have. It is a ratio of small change in the collector current, that is delta IC, to the small change in base current, delta IB, is known as base current amplification factor, and it is denoted by beta, and therefore beta is equal to delta IC divided by delta IB, and the value of beta is in between 20 to 100. So this is about the beta, first amplification factor. Now base amplification factor, that is alpha. Now alpha is defined as, it is a ratio of small change in the collector current to small change in the emitter current. Alpha has always less than unity, that is 0.95 to 0.99, and it is defined in this fashion: alpha is equal to delta IC divided by delta IB. Now let us try to derive the relation between base current amplification factor and emitter current amplification factor. So this is the small derivation we have. Now we know that this is the famous relation we have: I is equal to IB plus IC, and as we know that, just we define beta is equal to IC divided by IB, and alpha is equal to IC divided by IE. So dividing numerator and denominator of equation number 3 by IB. So if I divide the numerator and denominator by IB, I will get alpha is equal to IC divided by IB divided by IE divided by IB. That is my equation number 4. If I put the value of IE from equation number 1, I will get alpha is equal to IC divided by IB as it is, and divided by, we substitute the value of IE, that is IB plus IC divided by IB, which is equal to IC divided by IB as it is, and IC divided by IB is equal to beta divided by 1 plus IC divided by IB, and IC divided by IB is equal to alpha. So I will get alpha is equal to directly beta divided by 1 plus beta. That is my equation number 5. Now beta in terms of alpha, we calculate the beta or value of the beta in terms of alpha. Now we know that the alpha is equal to beta divided by 1 plus beta. So cross multiplication, alpha plus alpha beta is equal to only beta, and I am interested in alpha. Alpha is equal to alpha on one side, everything on the other side. Alpha is equal to beta minus alpha beta, and therefore alpha is equal to beta is a common and remaining inside the bracket 1 minus alpha, and therefore beta is equal to alpha divided by 1 minus alpha. So I find out the beta in terms of alpha, and that is beta is equal to alpha divided by 1 minus alpha. That is my equation number 6. So these are the two values of alpha and beta. Now the input characteristics. Now the characteristic is a graph that tells us about the behavior of a device. Now the behavior of an electronics device is explained in terms of a voltage and current. So basic thing, the behavior of any electronics device can be explained in terms of a voltage and current. Now this figure shows the characteristics of a transistor under common emitter configuration. Now base to emitter voltage varies. So base to emitter voltage varies. So left hand side, base emitter voltage varies by the potentiometer, and collector emitter voltage is varies by adjusting another side potentiometer. Okay, so this is the potentiometer arrangement. Now input characteristics. So how can you plot the input characteristics? So I already plotted the input characteristics in the next figure. Now the curve plotted between base current IB against base emitter voltage VB by keeping VCE constant. So the input characteristics is nothing but the curve plotted between base current IB against base to emitter voltage VB by keeping VCE constant is called the input characteristics curve. For drawing the input characteristics, the reading of a base current is taken through the emitter and emitter voltage, that is emitter base voltage VB, at constant collector emitter voltage. So we plot the different sets for keeping the value of a VCE constant, vary the VB, observe the IB by keeping VCE constant, and we take the three sets by keeping VCE constant and plot the graph. And this is the graph which shows the input characteristics of a transistor under the common emitter configuration. Now this curve is similarly to the forward characteristics of a diode. What are the points we noted from this graph is that the curve is similarly to the forward characteristics of a diode. The base current increases with increasing emitter to base voltage VB, just I explained. The effect of a C does not cause any large deviation on the curve. Hence the effect of a change in VC on the input characteristic is ignored. Now we find the input resistance. The input resistance is the ratio in the change in the base emitter voltage to the change in the base current, that is delta IB, by keeping constant collector emitter voltage, that is VCE, and which is known as a input resistance, and that is denoted by RI. Output characteristics. So this is the output characteristics of a transistor. Now output characteristic is a curve which is drawn between the collector current IC versus the collector emitter voltage VC at constant base current IB. So we keep the constant base current IB for different value of a IC and different value of a VCE. Now in case of the transistor, output characteristic of a transistor, if you see the figure, we have a three region. First region, active region, saturation region, and cutoff region, which I have shown by the dotted lines. So these are the three regions. Now in the active region, the collector current increases slightly as collector to emitter voltage increases. Okay. The value of a collector current IC increases with the increase in VC at a constant value of a IB, and that is the value of a beta also increases in case of the active region. Now in case of the saturation region, the collector current become independent and free from the input current IB. So in this case, in case of the active region, emitter base junction is a forward bias and collector base junction is also forward bias. So in this mode, the transistor has very large value of a current. Now cutoff region, the transistor operated in this mode when it is used as a closed circuit, and therefore there is large change in the collector current IC with small change in VC. The region, both the junctions are reverse bias. So in the cutoff region, both junctions are in the reverse bias, and that's why in this mode transistor has a zero current. Therefore transistor used as an open switch, since the collector base junction is a reverse bias. Now last one is output resistance in case of the output characteristic, as you see in the input resistance. So output resistance is the ratio of variation in the collector emitter voltage to the collector emitter current is known as output resistance. So that output resistance RO is equal to delta VCE divided by delta IC, keeping IB constant. So that is the output characteristic of a transistor.